right, so working out just a few of these possibly buffer, possibly not buffer practice questions. I kind of threw in a couple of not buffer questions just to see if you're paying attention, so make sure you pay attention. First one, explain how nitric acid and sodium acetate can be used to make a buffer solution, and then illustrate your answer using a chemical equation. Well, if we have nitric acid, HNO3, and we have sodium acetate, how can we use this to make a buffer solution? Well, we need to look at what we have. We have HNO3. That's a strong acid. We have NaCH3COO. Well, the sodium is going to be a neutral ion, so it's not really going to contribute to the acidity or basicity of this particular salt. But this acetate ion, that is the conjugate base of a weak acid, so this is a weak base. So how can we use nitric acid and sodium acetate to make a buffer solution? Well, when you have a strong acid and a weak base, to make a buffer solution, you need to make sure that you have an excess of the weak base. So you would say, make a solution containing an excess of the sodium acetate and a little bit of the nitric acid, and you would end up with a buffer solution. And it would ionize. Remember that nitrate, that's just another neutral ion. It's just going to cancel out, and so it would ionize, and you would have the hydrogen ion plus the acetate ion, giving you acetic acid. And so this would be your buffer solution. As long as you have an excess of that weak base, then you'll have a combination of conjugate base and weak acid, and that would be your buffer solution. Okay, what is the pH of a solution made by mixing 1 liter 0.1 molar HCl and 2 liters of 0.06 molar NaOH? So what is the pH of? We have two chemicals coming together, and hopefully you're getting to the point that you can recognize your strong acids and strong bases. And I see that I have strong acid plus strong base. So am I dealing with a buffer situation here? If you look back at that table, you would realize, no, you're not. I'm just dealing with a straight up neutralization reaction of strong acid and strong base. So HCl, NaOH, it's going to give me NaCl and water. Of course, since this is strong acid, strong base reaction, you know that this is just going to reduce down to hydrogen ion, hydroxide ion, and water. So I need to figure out, I have 1 liter of 0.1 molar HCl. I have 2 liters, sorry, I forgot to put my 0 in there, 2 liters of 0.06 molar NaOH. I have an amount of both reactants, so I need to figure out which one's limiting. So I'm going to convert both of these guys to moles. Well, if I have 1 liter of 0.1 molar, well, then I have 0.1 mole. If I have 2 liters of 0.06 molar, well, I have 0.12 moles. Wait. 0.012. I'm having a brain fart here. Do not tell anyone that I'm putting this into the calculator. Yeah, okay, it's 0.12 moles. It's Friday afternoon, so my brain is starting to shut off. So looking at these two guys, which one is your limiting reactant? Well, it's the one that you have the fewest number of moles. So this is your limiting reactant, which means all of this is going to react. 0.1 moles of this is going to react. So if we take that out because it's reacted, that leaves us with 0.02 excuse me, moles of this. And so to figure out the pH of this solution, we see that we have 0.02 moles of hydroxide ion. Well, I can very easily turn this back into a concentration, figure out my pOH, and then subtract that from 14 to find the pH. So I'm in moles. I have a total of 1 liter plus 2 liters, 3 liters of solution. So 0.02 divided by 3 gives me a hydroxide ion concentration of 0.00667, and so that means my pOH is negative log of that, which is equal to 2.18. But remember, this is pOH, and the question asked for pH. So pH is equal to 14 minus this, or 11.8. I guess we can carry it out 2 decimal places, can't we? 11.82. Okay, what's the pH of a solution made by mixing 1 liter of 0.11 molar HCl with 3 liters of 0.08 molar NaF? So again, let's see what we have. We have a strong acid plus sodium fluoride. Well, sodium is a neutral ion, but fluoride is the anion of a weak acid, which makes it a weak base. So we could have a buffer, or we could just have excess of strong acid, so we need to figure that out. So we take HCl, add to that some sodium fluoride, and we're going to make sodium chloride and the weak acid HF. Chlorine ions cancel out, sodium ions cancel out, so that your net ionic is H plus F minus gives us HF. So now I'm going to look at what I have, find out what my limiting reactant is. So I have 1 liter of 0.11 molar of the hydrochloric acid. I have 3 liters of 0.08 molar sodium fluoride. So this works out to 0.11 moles. This works out to 0.24 moles. So who's the limiting reactant? The hydrochloric acid is your limiting reactant. So all of this is going to get used up. So this is gone. 0.11 moles of the fluoride ion will be used up, leaving us with 0.13 moles left over, and that means we're going to produce 0.11 moles of the hydrogen fluoride, or hydrofluoric acid in this case, since we're aqueous. So that tells me, since I have an excess of my weak base with a limiting amount of my acid, that tells me that I have a buffer. Yay, buffer! Go back to that table if you forgot that. Excess weak base plus a little bit of strong acid means buffer. So to calculate the pH of a buffer, I'm going to take the pKa of hydrofluoric acid, and I'm going to add to that the log of my base concentration over my acid concentration. Of course, to do this, we need to know the pKa of hydrofluoric acid. And of course, I did not prepare in advance and look that up before I started this video. So give me just a second to look that up. Let's see, the Ka of HF is equal to, I'm just looking this up in a book, 6.8 times 10 to the negative 4. So plugging this in over here, pH is what we're solving for. pKa is going to be equal to the negative log of the Ka, 6.8 times 10 to the negative 4, plus the log of my base concentration is 0.13. My acid concentration is 0.11. And so this is going to work out to plug this into the calculator, and you get that the pH is 3.24, and there you go. Okay, I might have time to spit out one more before the bell rings, but if the bell rings in the middle of this particular problem, I apologize in advance. Just ignore it and have some sympathy for how annoying it is that I have to hear this thing 9 times in a day. Okay, what is the pH of a solution made by mixing 1 liter 0.2 molar nitric acid, 2 liter 0.1 molar sodium cyanide? Ooh, killer stuff here. Again, what do we have? Actually, you know what? I'm going to skip this one and do this one, because this one is exactly like what we just did, and I want to do something a little different. So we're going to do this one. Hey, look, it's acetic acid again. We've got 0.25 liters of 0.2 molar acetic acid with 1 liter 0.3 molar potassium acetate. So what do we have going on here? Well, we have a weak acid here. Potassium acetate, well, that's a weak base because the potassium is a neutral ion. So we have a weak acid and its conjugate base. We have a straight up buffer problem. So I'm going to go ahead and write out my reaction. And hydrogen ion plus the acetate ion. And I need to find my concentrations of my acid and my base. But I can't just use these concentrations because these are the concentrations before they mixed. Once they mix, the concentrations are a little different because my volumes are different. So I have 2.5 liters of 0.2 molar of the acetic acid. I have 1 liter of 0.3 molar potassium acetate. So figure out how many moles this is. This first one works out to 0.5 moles, and this one, 1 liter, of course, works out to 0.3 moles. And now we need to take this and divide it by our volume that we have now, which is 3.5, to find our new concentration. So the concentration of my acid is going to be 0.5 divided by 3.5, or 0.143 molar. And this one's going to be 0.3 divided by 3.5, or 0.0857 molar. Now I said pH of a buffer solution. There's that bell. pH equals pKa plus the log, I told you it was a bad bell, of base over acid. So plug these numbers in. If you haven't got this sucker memorized by now, I'm surprised, but the Ka of acetic acid is 1.8 times 10 to the negative 5. So we take the pKa, which is the negative log of the Ka, 1.8 times 10 to the negative 5, plus the log of the base concentration, which is this guy, so 0.0857, divided by the concentration of the acid, which is 0.143. Plug all this into the calculator, and you end up with 4.52. Now, I forgot to tell you on the last one, but you know how there's always tricks to kind of help you know that you're on the right track with the numbers? You know, does this number make sense? Well, if you look at the pKa of acetic acid is 4.74. And if you look at this, then you can tell whether or not you're good to go. So if we were at the equivalence point, meaning the pH and the pKa are equal because the acid and the base concentrations cancel each other out, and this just works down to 0. If the acid and base concentrations were equal, then pH would equal pKa 4.74. If the base concentration was higher, then we would expect our resulting answer to be higher than the pKa. If our acid concentration is higher, then we would expect our final answer to be lower than the pKa. Because whenever you're taking the log of a number greater than 1, you end up with a positive number. And when you take the log of a number less than 1, meaning the denominator is bigger, then you end up with a negative number. So in this case, do we have a higher concentration of acid or base? Well, higher concentration belongs to the acid, so we should expect our final answer to be a little bit less than our pKa, which 4.52 is less than 4.74. So there you go. If you have any questions about buffers, feel free to email me, or if you are one of my children, just ask me in class. Y'all have an awesome, awesome weekend. Or if you're watching this in the future and it's Monday, I'm sorry, I just got your hopes up about the weekend. Have an awesome rest of your day.